As I worked through lesson 9, when are they the same, I realized that I was always calculating the difference in the y-intercepts, and I was calculating the difference in the slopes of the two lines that I was working with. Now I went directly to writing linear equations in the form of y equals mx plus b, and graphing those equations and using that to answer many of the activities from lessons 1 through actually lessons 9. I actually did this before the authors start to introduce this idea. Now this is coming up in the text, in the curriculum, in that the authors are going to get into the same idea as as we go into lesson 10. So now we're going to start looking at lines, and we're going to start graphing lines, and we're going to start looking at systems of equations and solving those systems of equations. Now we've been doing that all along, because I didn't want this to be a surprise to anybody, and we already had the basic understanding of how to do this, and so I wanted to use it right away. And so I'm going to be very interested to see if the authors describe what's going on as they solve systems of equations in the same way or in a similar way that I have started to think about this. So what I did is I chose a point at random out here, just 11.113. And I also chose 2 points along the y-axis randomly, and then I connected those points. I drew the line here and drew the line here, and the line of intersection is the first point that I chose. And I wrote the equations for each of these lines. We'll get into that in just a second. But then what I did is I decided, well, what if I slide this line down here and I slide this line up here? What happens, and am I following the same kind of pattern in talking about the difference in the y-intercepts, this difference right here, and the difference in the slopes, so the difference between 6/11 and a negative 2/11. Am I following that same path or using that same language to describe that? And then I came up with a general way of basically saying the same thing. So here are the lines where I just reversed the y-intercepts. So I slid this line was down here, and I slid it up here, and this line was up here, and I slid it down here. So here's the first slide, the first example, and here's the second. So I'm just sliding this line up. So just focus on that line for a minute. That slides up, and then focus on this line slides down. All right. So first of all, let's write the equation for each of these lines. And so you know that the y-intercept is 5 and the y-intercept is negative 3. And so you just have to figure out the slope. So if I go out here 11 units and then down 2 units, that's a negative 2. So that's the length along the y-axis is a negative 2 over the length along the x-axis is 11. So that's a negative 2/11. So this is a negative 2/11. And what the student has to start to understand, and I think they can use some practice on this, this is kind of a tough thing to realize, is that this length, this relationship, negative 2/11, this negative 2 over this 11 is the same length as this right here. That's per unit. So this length right here is a negative 2/11. And it's really hard to see. It's right there. This length from 5 to right here is a negative 2/11. Likewise, if you figure out the slope for this line, you go out 11 units. So this is nice work with fractions as well. So because I chose these numbers at random, the fractions are a little bit messy. They're 11ths, but you're going to see that's okay to work with. If you just keep it as a fraction, refrain from changing it to a decimal, then it easily, you can easily calculate with that fraction as you solve these. All right, so you go out along the x-axis 11 units, and this now is a positive 6. That's a positive 6 over 11. So that's 6/11, or 6 over 11. And notice that that's this length right here. This length is 6/11 of this unit y, this 1 unit along the y-axis. So 6/11 of this 1 unit. This is 2/11 of this 1 unit, but this is in the negative direction. This is in a positive direction. So now something else that happens as you go through and describe these problems is that change in 1 unit x is the difference between this length right here and this length right here. So you take this length and you subtract it from this length, and that gives you what this distance is now, what the difference is now from this point to this point. And it turns out, and we'll get into this in just a second, that this 6/11 minus this -2/11, you end up adding the 2/11. So again, just continuous work with things that the students struggle with. So now we're working with positive and negative numbers, and you're realizing, and fractions as well, so you're realizing that 6/11 minus a -2/11. What's the difference between them? It's going to be a positive 8/11. So 6/11 minus a -2/11 is the same as 6/11 plus this 2/11. So now you're going to add the 6/11 plus this 2/11, and that visually shows you that this distance is being reduced by that amount, 8/11. And then you do that again. This distance is reduced by another 8/11. This distance is reduced by another 8/11. I'm getting ahead of myself a little bit. All right, so what I did is in order to solve for this x, which we know is going to be 11, I set these two equations equal to each other. They're both equal to y, so you can just take them and set them equal to each other. So this is what the authors have done throughout this unit up to lesson 9, is they've worked with linear equations in a single variable. That is even hard for me to understand. I don't understand how you can have a linear equation in one variable, but we'll have a discussion about that later. All right, so you set them equal to each other, and you begin to solve, and you realize, well, one calculation you're going to make is what's the difference between these two slopes, and another calculation you're going to make is what's the difference between these two y-intercepts. So you start making the calculation, and I'm going to always calculate the difference in the slopes. In other words, get the x values on the same side of the equation by ending up with a positive x. I'm going to look at these two values, and I'm going to realize that if I add a -2/11 x, then I'm going to add a positive, I'm sorry, if I have a -2/11 x, I'm going to get rid of that by adding its additive inverse. And I always work with additive inverses, so I always change all the subtraction to addition, and I always add additive inverses. It just makes my life easier, and I never get confused with positive and negative numbers. So to get rid of this -2/11 x, you're going to add its additive inverse, which is a positive 2/11 x. You do the same thing over here. So this is going to end up being a positive x. It's going to end up being a positive 8/11 x. So let's do that first. And by doing it that way, the other thing is I don't ever work in columns. That's not a mathematical operation. It's not a mathematical equation to set this up as, oh, it's a -2/11, so I'm just right here, I'm going to add 2/11, and right here I'm going to add another 2/11. You get the same answer, but you miss the stepwise fashion of solving equations, which is what students are going to need as they get into later grades. So keep this as an equation. If you use Docera, you can change the colors and show what you do on one side. It has to be done on the other side to keep it balanced. That's kind of a nice thing. Anyway, so this is the difference right here in the two slopes. It's 6/11 plus 2/11. So it's this 6/11 x actually minus a -2/11 x. But to subtract a -2/11, that's the same as adding a positive 2/11. So the language, the discussion, again, includes many things that students get confused on. So you're continually reinforcing that language as you go through the problems. So this is a positive 8/11 x. And that is the difference in the slopes. It's how much the gap, this difference between these two y-intercepts, how much this is closed for each unit x. So this is 8/11 x closer. This is 8 Yeah, so 1 times 8/11. So this is 8/11 closer. This is 8/11 closer. This is 8/11 closer. This is 8/11 closer. And so we're going to use that in just a moment. So this gap is getting closer by 8/11 for each unit x. It's 8/11 actually along the y-axis. For each unit x, how many times can you do that? We're going to find out in a moment that you can do that 11 times before that gap is completely closed, which is the point of intersection. All right. So the difference in the slopes is how much this gap is closed for each unit x. 8/11, 8/11, 8/11, 8/11, and so on. So now on the other side of the equation, I'm going to figure out this difference in the y-intercepts. So I'm left with 5 over here. That's this y-intercept, and a -3 over here. That's this y-intercept. So how far are they apart? Well, it's this 5 minus this -3. What's the difference between 5 and -3? It's 5 minus a -3. Let's subtract a negative. That's the same as adding a positive. So now I'm going to add the additive inverse. 5 plus a +3. And over here, this is a -3 plus a +3 to get rid of that. So right here, this is the difference in the y-intercepts. How far are those y-intercepts away from each other? What's the difference? What's the distance between them? And that distance is 8 units. It's 5 units and another 8 units, actually. This goes in a positive direction. Yeah, well, don't have to go into detail why that is, but this is 3 units and another 5 units. So the difference in the y-intercepts is 8. It's going to be a +8. And so now you have this +8 units, and you have 8/11 x. That this is reduced by that length, 8/11 for each unit x. Well, how many times can you take 8/11 out of 8? How many times can you do that? That's going to be the value of x to get to the point of intersection, because you're closing this gap 8/11 of a unit at a time. Eventually, you're going to get to this point right here. So 8 units difference in y-intercept. The difference is covered in 8/11 unit steps. A little bit hard on the language here, but I'm going to go 8/11 closer, 8/11 closer, 8/11 closer. I'm starting out with 8 units. So 8 divided by those 8/11 is going to tell me how many times I can move in this direction until they intersect, until basically you're using this all up. So this is where a context around this problem is going to make it even more clear what's going on. So these things will come together. So the difference is covered in 8/11 unit steps for each unit x. Well, how do you calculate that? Now, normally, if I wasn't talking about this context, I would say you multiply by the multiplicative inverse, which is 11/8, which is right here. This is what you end up doing anyway. So again, practice on how you deal with the division with fractions. So there's no simple rule to follow. There's no flipping it and switching or whatever people say to try to remember. You just multiply by the multiplicative inverse. So 8 divided by 8/11 is the same as multiplying by 11/8. This 8 times that 11/8 right here, and that equals 11, which is x. Here's x right out here, which is 11. So the intersection is at 11 units along the x-axis. Now to solve equations, just real quick, actually I think let me say that. So to move the x's to one side and move the y-intercepts to the other side, I always use the additive inverse. And then once I get to this point, I always use the multiplicative inverse. So I'm always just thinking about 2 things, additive inverse and multiplicative inverse. Just makes life easier to simplify the solutions in that way. All right, so let's look at the other lines, so where they intersect over here. So the difference in the y-intercepts is still 8 units. These are 8 units apart. But is that going to be a positive 8 or a negative 8? So we're going to figure out how to keep that straight. So calculate the difference in the slopes to have a positive result. So I'm going to set these two equations equal to each other, and I'm going to calculate this so I end up with a positive amount of x. So I'm going to subtract this negative 2/11 x, so 6/11 minus a negative 2/11, so 6/11 here. I'm going to set this up in just a second, but if you're just visually looking at this, you're not really trying to solve equations, you just look at the slopes, you're going to subtract this negative 2/11 from 6/11, and remember that's the same as adding 2/11. So this is going to equal a difference of 8/11. So now I'm moving away from setting this up rigorously as just blindly solving an equation to find this point of intersection, but reasoning through this difference in slope is going to be 8/11, and how far apart are the y-intercepts? They are 8 units apart. The 8-unit gap in the y-intercepts is closed 8/11 of a unit for each unit x. So we did that before. So every time you go 1 unit x, this gap is closed by this difference in the slopes. It's closed by that 8/11. So again, it's the same calculation. How many times can I take that 8/11 out of 8? I can take that out 11 times. 8 divided by that 8/11 is the same as multiplying by the multiplicative inverse. You use the inverse operation, and you use the the multiplicative inverse of 8/11. So that's 8 times 11/8, which equals 11. Now notice that this 11 is a negative 11. And you know that the 8/11 has to be positive because you set it up that way. 6/11 minus a negative 2/11. So that 8 right here has to be negative. But x is a negative 11, so the 8 must be a negative 8. So let's go through this calculation, setting up the equations equal to each other and just kind of blindly calculate it. You're going to see why it's negative 8. So here are the equations set equal to each other. So I'm going to move all the x's to one side where it's going to be positive. So that means I'm going to add a positive 2/11 here and here. So a positive 2/11. So this equals 8/11. This goes away. There's the 8/11. So now we have 8/11 plus 5 equals negative 3. So now on the other side, we're going to get the y-intercepts to the other side. That means I have to add a negative 5 here. Well, if I add a negative 5 here, I have to add a negative 5 here. So this becomes a negative 8. So 8/11 equals negative 8. And emphasize that's a negative 8. And so then when you solve, or you figure out negative 8, I have a negative 8 gap here. So the difference between 5 and negative 3 is actually a negative 8. I'm going to go this way in the negative direction. So to figure out how many times I can take 8/11 out of that negative 8, you divide. So 8/11 units, each unit x, I have a gap of negative 8. So I'm going to divide that negative 8 by 8/11. And so I'm going to end up multiplying by the multiplicative inverse, 11/8. That's how you would solve this anyway. You'd multiply by 11/8, multiply negative 8 times 11/8. It's right here. And you end up with negative 11. That's x. Now, this is starting to get lengthy and it's starting to get confusing. But the more and more you go over it with each of these problems, the simpler it gets, the more obvious it gets of what you're looking at. You're looking at the gap between these two y-intercepts, and you're looking at the difference in these slopes. And you're figuring out how many times that difference in the slopes fits into this gap between the two y-intercepts. That's division. Just to go back here, the first step is to get the x's on one side, add additive inverses to the left to get positive x's. So I wanted to have positive x's, so I added the additive inverse to the left side and to the right side for that matter to get rid of this. And then next, you work on the other side to add the additive inverse to the right to get the x's by themselves, but also you calculate what the difference in these y-intercepts is by doing that. So one side, add the additive inverse to get the x's. Onto one side, add the additive inverse to the other side to another way of saying that is to get all the y-intercepts to the, in this case, the right side. All right, so now I try to come up with a general way of looking at this. So I'm just going to use M1 and M2 for the slopes and B1 and B2 for the y-intercepts. So if you write these equations and you set them equal to each other, then you're going to subtract M2 x's from M1 x's. So M1 minus M2, and those are x's. And then on the other side, now you're going to subtract the B1 from the B2. So this is going to become the proper sign. It's either going to be positive or negative. In this case, it's going to be negative because x is going to end up being negative. Remember, you're going to calculate this, so this ends up being a positive value. So that forces on this side to find the difference between B2 and B1. So this is going to be a negative value in this example. So you're going to step this way. So this slope right here, M1, and you're going to step up this way. So that's this slope right here, M2. And you're going to find that that difference, oh, and actually then you're going to calculate what the difference in the y-intercepts is, this difference right here. So now you're going to calculate the difference each time. It's going to get less. It's going to shorten by this difference right here. This length right here and this length right here. You actually add them together because you're subtracting a negative amount up here. So it gets shorter by, our example was 8/11, gets shorter, and gone. It will continue to get shorter by that amount until it intersects. So choose M1 minus M2 or M2 minus M1. That results in a positive x. So you just have to look at it and figure out what difference do I want to calculate to make x positive. And then you do the difference or change is the number of units along the y-axis that the lines get closer for each unit x. So that difference is the number of units along the y-axis. In our example, it was 8/11. That the lines get closer for each unit x. So these lines get closer by that amount, gets closer by that same amount. 8/11 gets closer by that same amount, gets closer by that same amount. So for each unit x, so how many times can you do that until these lines intersect? That answer in our problem previously was 11. And a couple of phrases that I've been using, you want to close this gap or cover the distance in the y-intercepts. So this is getting closer, closer, closer. So I've talked about this as closing the gap or just covering this distance. How many 8/11 does it take in our problem? How many 8/11 does it take to cover this distance? It took 11 of them. All right, then on this side, this is the length along the y-axis. This is the difference in the y-intercepts. Difference in the y-intercepts, the length that has to be covered for the lines to intersect. So this length has to be removed or be covered for these two lines to intersect down here. So x is equal to b2 minus b1. So this difference, this length right here, divided by how much the slope, how much the difference in the slope is, because that's how much this length is covered for each unit x. So x is the number of times you can do that, the number of times you can take that difference in slope away from this length right here. And it's getting hard to talk about. The number of times that the difference in the slope, and I tried to show this here. I put a larger dot here, that's this length right here, and a smaller dot here, that's this length right here. How many times can you take that length out of this difference? That's going to be x, can be removed from the length between the y-intercepts. And I have another way of showing this right now. So I'm going to zoom in on this. So this is the same image. This is this right here, just zoomed in. So it's this length right here, and it's this length right here. So what I'm going to do is add those two lengths together and then take them away from this line. So if I do that, if I take this length away from this pink line, I'm going to end up with this length. So this length now has this length removed. So this is M1, this is this length, same as this length. This is M2, it's this length right here. I just moved it up here, it's this length. So this length is going to be removed, and you're going to end up with this length. That same length, this length right here, is going to be removed, and you end up with this length. That same length is removed, you end up with this one, and so on. This length is removed. This length is subtracted away or removed. This length, same length. How many times can I do that till these lines intersect? And notice this last one, it is that length. One more time, and that gets you to this negative 11. So you can do that 11 times, but it's going in the negative direction. And zoom in on this just for a moment. So this is the slope. This is this length right here is the slope for 1 unit. And this is the slope for 1 unit. And these, the difference between them, you end up adding their values. Because this M2 is a negative slope. This M1 is a positive slope, actually. You go to the left and then down, that's a positive slope. But this one, you go to the left, but then up. That is a negative slope, because it's a negative, it's a positive value over a negative value. So this is a negative slope, this is a positive slope, so the difference, you end up adding them together. I got a little bit hard to explain, but it's an attempt. It's a way of thinking about this, and I really actually have trouble thinking about these problems in any other way these days, where I'm looking at the difference in y-intercepts, I'm looking at the difference in the slopes, and I'm trying to figure out, okay, how many times can I take this difference in the slopes away from this distance or this difference in the y-intercepts? That answer is x, and then you just take that x value, put that back in the equation, and you get the value for y.